Hello everyone, welcome back to my channel. Today we have announced the third early access version of QuantumVITAS, and as usual you could go to the official website and download it from the download page. All of the links here are updated, so that's the newest version. What you could also do is to go to the GitHub page and then to the releases, and v0.3.0, that would be the newest version now. You can see the feature list that we have implemented some user experience improvements. For example, to ask the user to save the project when they close the project or the application, and also add no symmetry option for molecular dynamics calculation. And those are the comments that I got from you guys. So thank you everyone for your support and comments, and they are very helpful. One of the central new feature of this version is the projected tensor state and projected band structure calculation that projects to the atomic orbitals. This is basically something that you often see in the literature, but in Quantum Espresso it is not so straightforward to do manually. And now in QuantumVITAS you could very easily do that, which I will show you in a minute. Also here I would like to introduce you the wiki that I start to work on the documentation of QuantumVITAS. For example, this is the home, and you could go to the quick start here, and this is basically the same quick start as in the official website, and there are also some useful hacks. So we have implemented renaming the project and calculation in the program, but not yet deleting or duplicating calculations of projects. So one of the hacks would be that you could close the program and then do it manually from your operating system, and then run the program again. And actually it is designed that it will recognize those changes in the folders. For the conversion from zip file or VASP postcard to Quantum Espresso input file, for QuantumVITAS you could check the online tool from Materials Clouds, and also for the K-Path you could also use the tool from Materials Clouds. So I will also post more useful hacks and some detailed documentation of QuantumVITAS. So this wiki would be something that is useful. Okay, so now I would like to show you QuantumVITAS here. Okay. I will make two examples. One is Graphene. Let's open Graphene. We could show more atoms, more unit cells, and you see the honeycomb structure of Graphene. Now, one feature is that you could click on the atom and it will tell you which atom you are selecting, what is the chemical element, and what is the position in angstrom. And this also works in the case of a supercell like this. And you see that it shows you the position and the atom here. Okay, so what I have shown you before is the band structure of graphene, where there is a Dirac cone. And what I'm going to show you now is what is the orbital character of this Dirac cone. So what we could do, basically the self-consistency calculation is the same. For the bands calculation, we go from gamma to k to m to gamma. And then in the post-processing, we turn on the projection to the atomic orbitals, and now we could do the calculation directly, and we will just wait 1 second. Okay, now it's finished. We refresh the file list, and you see that apart from the normal bands.out.gnu file, that is the normal band structure, you also have something like pbands.project.wfc. And now you also have some options here that you could choose. The 2s orbital of carbon atoms are shown, and the larger the circle is, and the bigger the contribution is. So you see that the contribution is more or less here at the bottom, which is the bonding state, and here at the top, which is the anti-bonding state. And for all other lines without circles, basically there is no contribution from carbon 2s. And now the interesting thing is that for carbon pz orbital, it is near the Fermi level, and then it forms the Dirac cone. And this is easy to understand because the pz orbital forms a big pi bond, basically in graphene, which contributes to the Dirac cone. Okay, so you could also see what is the px and py orbital. And basically px and py are here, which has no contribution to the Dirac cone. So here it's very easy. We do the calculation and it correctly shows us that the Dirac cone basically consists of the pz orbital of the carbon atoms. And here you see that there is another option here. By default it is per element. Basically it means that we sum up the contribution from same type of atom, But you could also do per atom, and then you will have here the first 4 are carbon number 1 and the last 4 are carbon number 2. Yeah, and in this case you see that the circles are smaller because basically this is half the intensity. What we could do is that we increase the marker size, for example, to 2.5 to make it larger, or even we scale it to 3, make it even larger. And then you see that for carbon 1 and carbon 2, the s orbital is the same. The z orbital contribution is also the same. This is because of the symmetry of the lattice. Okay, so now I have shown you it's very easy to use QuantumVITAS to project the band structure to the atomic orbitals. And what I'm going to show you next is the projection of the density of state of silicon to the atomic orbitals. And you see that now we have another tab here for the density of state calculation, and we just need to turn on the calculation of the projected density of state here, and then we start the calculation. And this should also just take a few seconds. Okay, now it's finished. We refresh the file list and you see that this is a density of state calculation. And on the left hand side, you already see the 4 PDOS files for the first silicon atom and the second silicon atom. Yeah. So this is the first silicon atom s orbital, first silicon atom p orbital, second silicon atom s orbital, second silicon atom p orbital. In case you want to sum up the contribution from atoms of the same type, you could press here, sum PDOS, and then after a few seconds, refresh, and you will see that it generates 2 files. Yeah, one is the s orbital of the sum of all silicon atoms, and the second is the p orbital of silicon atoms. And basically you see that the 3 p orbitals has the same projected density state. This is because of the sp3 hybridization of silicon-silicon bonds. So this is basically the projected bands and projected density state calculation. What I have also implemented was that you could now rename the calculation as well as the project here. What you do is that if you want to rename the calculation, you right click on the calculation and rename. Yeah. For example, we rename that to bands 2. Yeah, for example, and we press OK, and then this changes to bands 2. You could also rename a project. For that, you have to click on the basically here, and then right click, rename. And for example, we rename that to Silicon 1. And if we close the project, it will ask you whether you want to save the project or not. In this case, there's nothing to save, so we press no. And also if we close the application, it will ask you whether you want to save all of the projects. You could press here, save all, and exit. You could also exit without saving. And in case you don't want to close the application anymore, you could press here, cancel, or here. And then you are back to the workspace. Yeah. Okay. So in this video, I've shown you the new features of QuantumVITAS 0.3.0. And thank you everyone for your support. Now I think QuantumVITAS has evolved quite a lot and covers a lot of features of Quantum Espresso, maybe most features that are usually used. But as usual, I welcome any comments, bug report, suggestions, things that you want to implement on your side, and that proves to be very helpful. Yeah. Okay, so thank you for watching, and I hope to see you next time.